Okay, good morning, good afternoon, everyone. It's my pleasure to introduce Daniel Smertnig from University of Graz, and he'll talk about height gap theorem for coefficients of Mahler functions. Thank you, Daniel, for coming, and please.
Well, thank you very much, of course, for having me here. It's a pleasure to speak in this seminar. I was told by Michael to expect a somewhat broad audience, and I think also that in some sense my talk is not exactly maybe in your area, so I will try to give a bit of background also. But the main topic will be this paper, a height gap theorem for coefficients of Mahler functions that we did together with Boris Adamczewski and Jason Bell. So what I want to do is first I want to recall or introduce the definition of Mahler functions and give some examples. And then these Mahler functions come up in two contexts basically. The first is in transcendence results and transcendence theory. And the second one is in connection with theoretical computer science, in connection with automatic and K-regular series. And I want to talk about that briefly. And then in the final section, I will actually get to the theorem that we proved. So what is a Mahler function? So we actually only consider power series Mahler functions. So we fix an integer k larger than or equal to 2. And then a power series is called a k-Mahler function, or short just M function, if it satisfies an equation of this form. So this looks a bit like a differential equation, but instead of a differential operator, we have this Mahler operator or k-Mahler operator, which substitutes z raised to the power k for z. And then we have a linear, well, yeah, a linear equation with polynomial coefficients in iterates of that operator. And of course, the equation should be somehow non-trivial. So say P0 and PD should be non-zero. And this is a k-Mahler equation of degree d. There is a particularly interesting type of these equations which behave better when this leading coefficient P0 is actually a constant, or say 1. And then one knows that these power series are always analytic in a neighborhood of 0, in a small neighborhood of 0. And one can use this recursion to extend this to show that they are meromorphic in the open unit disk. And this is true for every absolute value. So I'm not sure how familiar people here with different absolute value. It's definitely true for the usual absolute value, and we will also be needing the non-Archimedean ones in some sense. But so they are essential, but it's not too important to know about them here. So that is what the Mahler function is. And then from this functional equation, one can also derive a recurrence for the coefficients, at least for sufficiently large n. You get the recurrence of this type. This comes from the P0 coefficient, the linear part, and then this f substituted z to the ki give you this kind of coefficients here, where we set aq to be 0 if q is not an integer. It's not really important what this recurrence is. It's just important that there is a recurrence on the coefficients. So there's some kind of a combinatorial structure on the sequence of coefficients. And what one sees.
What is S here?
I didn't specify that. So that's the degree of P0, but actually one should first reduce to a particular kind where P0 does not have 0 as a root. This is, so in this equation, one can always reduce to P0 at 0 not equal to 0, but one might lose some initial coefficients.
So if it's Becker, then what S is what?
Then S is 0.
Yeah.
Well, okay, sorry. So it should actually be the maximum of the degrees of the polynomials, because we have the same S here. So then S might be, so if it's Becker, then this term is 0. That's the correct statement.
Okay.
This first term.
Well, thank you.
Okay. Okay, and the point is that if you have a Mahler equation and you give sufficiently many initial coefficients of a solution, then you can compute all the other coefficients recursively. In particular, the coefficients of such a solution. So we start out with them being algebraic integers here in Q bar, but in fact, they're always contained in a finitely generated field extension of Q. So they are always contained in a number field. Some examples of Mahler functions, well, every rational power series. So a power series expansion of a rational function without a pole at 0 is always k Mahler for every k. Say this geometric series 1 over 1 minus 2z. More interestingly, you can take an infinite product of such a type of series where now instead of z, you have z raised to k to the n and take the product over all n larger than or equal to 0. This still gives a m function. And for this one, because so here the n is equals 0 term is again this geometric series, the coefficients are at least as large as 2 to the n, so they grow exponentially fast. Another thing is if instead of 2 here you take 1, you get a different m function. And here you can check just by expanding this formally on the left that the coefficients an now count the number of partitions of n into kth power. So the number of ways that you can write n as a sum of powers of k where the order is disregarded. And here one knows originally by result of Mahler, also the asymptotics of the coefficients. So log of an behaves asymptotically like log squared n divided by a constant. Another example is if you fix a prime and you take as coefficients the p-adic valuation of n factorial, then this gives you a p Mahler function. And we know that the asymptotic growth is like n over p minus 1. Another one is you could take a number n and you expand it in base k and take the sum of digits in base k. This gives you a k Mahler function, or a slight variation on that. Instead of taking the sum of digits, you take the parity in the binary expansion. So if n has an odd number of ones in the binary expansion, you make it 1 and you make it a 0 if it has an even number of ones. This is the 2 sequence, and this gives you a 2 Mahler function if you take it as the sequence of coefficients of a power series. So these are some examples of k Mahler series with different kind of growth. I didn't say it for the last two, but the sum of digits is of course log n, and for the 2 sequence you just get 0 and 1. So here you have finitely many coefficients. Now, where did these m functions first appear? They were introduced in the 20s by Mahler in the context of transcendence theory. So his basic idea is that if you plug in an algebraic number into such a function, you should get a transcendental number. Then they were not so popular for some time, but then Cobham in 1968, when he worked on these k-automatic sequences in the context of theoretical computer science, proved that automatic sequences, if you take them as sequence of coefficients of a power series, are always m functions. And this was then popularized starting with the 80s and got somehow popular in theoretical computer science. And more recently, there are transcendence results on this series, in particular by Philippon and Adamczewski-Favershon, that now sort of mirror the theory of Siegel E functions. And the second part, which is somehow our motivation, is that, as we already saw, maybe interesting combinatorial sequences give rise to m functions. And then, of course, one can hope that there is an interesting interplay between, say, the arithmetic of and the properties of the coefficients, and maybe some structural properties of the equations, and so on. So let me recall some of the transcendence results in this context. The first thing that we need is, if we start with a Mahler equation of degree d, we can turn that, as for a differential equation, into a linear system of order 1. So we replace this one equation by system of equations, but we go from order d to 1. And now we have finitely many such m functions, f1 through fd, and an equation of the form that this vector of f1 through fd is somehow related to the same vector where we substitute z raised to k for z by an invertible matrix over the rational function field over the algebraic integers. Sorry, algebraic numbers, not integers. Okay, and then we call a point alpha regular if this matrix is and its inverse are well defined for all alpha raised to k to n, for all n larger than or equal to 0. So the entries of this matrix are rational functions, as is the case for the inverse, and we want to avoid all poles of these finitely many rational functions.
Question. Why do you make the F's power series? Why do you restrict power series?
Well, I think one could do this more generally also. Our motivation, or at least my motivation, comes from this k automatic and k regular sequences, to view them as coefficients of a power series and try to understand them as solutions of m functions. So in general, there's not all solutions will be power series.
Thank you.
Okay, and now here one of the main transcendence results is due to Nishioka from the 90s. I stated in a fairly general setting. Again, one can also just think about the usual absolute value, but here we have a number field and we have an absolute value, which say in case of the rational field, we could take the usual absolute value or one of the p-adic ones. And then we construct a field CV, which is both complete and algebraically closed and contains our field K. And this is where we work in, because this is algebraically closed and also complete. So we can talk about limits and so on. And then the statement is the following. If you have F1 through Fd that are solutions to a given Mahler system, and you have a point inside the unit circle that is non-zero, and that is regular with respect to the sequence, so that avoids singularities, so that the k to the n powers of it avoid singularities of this defining matrix A, then it's true that the transcendence degree of the field extension of k bar generated by the Fi's evaluated at the point alpha is the same as the transcendence degree of the field generated by these functions as an extension of the rational function field. So what this is saying is if you have an algebraic dependence at the point alpha, so at the values of the functions at the point alpha, then it must live already to some algebraic dependence on the power series themselves. And this was proved by Nishioka for the usual absolute value. And now recently, Fernandez used some generic framework of Philippon to show this also for function fields of positive characteristic. And this is not something that we need, but this approach also allows one to see that this works for non-Archimedean absolute values, which is something that we needed in the paper. This is this result of Nishioka, and then there's a more explicit lifting result of Adamczewski and Favachon. So we have a similar setting. We have F1 through Fd solutions of a Mahler system, and we have a non-zero point in the unit circle for some absolute value that is regular. And then they show that if we have a homogeneous polynomial that is satisfied by F1 alpha through Fd alpha, we can actually lift this particular polynomial to a relation on the power series. So more specifically, there exists a polynomial in various z and x1 through xd, which is homogeneous in x1 through xd, so that the power series satisfy this polynomial. And if you specialize for z equal to alpha, you get back this relation at the point alpha, this polynomial. So not just does a dependence lift, but it lifts in a specific way.
Excuse me, can you explain what a regular point for the Mahler system is?
Yes, let me go back to that. So we have this defining matrix A to the Z. A of z, and the
Okay.
entries are rational functions with coefficients in the algebraic numbers. And we need, so these have some poles.
Oh, right. Okay. I
And we
forgot.
want that alpha of raised to k to the n is not a pole in any of these rational functions, not for A of z and not for its inverse.
Okay. Sorry, I missed that.
Okay, no, that's
Thank
fine.
you.
That's good. It's good to recall it. I think others might have missed it.
Question.
Yes.
Is there a relation between transcendence properties that you mentioned in the previous slide and properties of sequences?
Uh,
The sequences of coefficients for the power series.
yes. I would not know that. I think that Jason is in the audience and might have something to say about that.
I couldn't make out the question. What was it?
If there's a relation between transcendence results and the sequence of coefficients.
I'm not sure. Yeah.
Well, I think there must be, because of the polynomial equation. If the F1 alpha and Fd alpha are dependent polynomially, then the coefficients for the F1 and Fd, in the power series, should have some dependence just deriving from this series. This equation, right? Now, how do you write it down? That's a different matter.
Yeah.
It may not be, the relation may not be entirely in terms of the coefficients as an infinite vector. Not as simple as that. But they could be interactions between parts of those series coefficients rather than always involving the entire coefficient series.
Mm-hmm.
Yeah.
The reason I ask is,
Don't know about this.
that you were thinking about sequences, right? Sequences of coefficients primarily.
Yes.
And I wonder how the transcendence result fits into that picture. Is it a lone result or it has a connection? So that's what I wanted to know.
Sorry, I don't quite get the question. So there are these transcendence results, they are known that I'm recalling now, and we are going to talk about the sequences of coefficients and their growth later on, and this second part is new.
Oh, okay.
I don't know if that answers your questions though.
I just wondered why you mentioned transcendence results.
Because we actually need them.
So there is a relation. Maybe
yes. So this would be the next slide, actually. Sorry. What we need is a very weak version of the transcendence result. We need to be able to lift linear equations. So what we need for one of these gaps is that if you have some solutions of a Mahler systems, which are linearly independent of over the rational field, then in some neighborhood of zero, you can evaluate the functions at this point alpha, and these evaluations are linearly independent over k bar. So
it seems
other words,
to be converse, isn't it? Originally you were lifting relations on the Fi alphas to the Fi z. But now it's the other way around. Is that right?
It's the contrapositive. So if I'm saying linearly independent here.
Right.
So if the Fi alpha have a linear dependence relation, then we can lift it to a linear dependence of the power series. This is how the result is used.
Yeah, okay, I got it. All right, thank you.
Okay, and this is why it's just a special case for linear relations.
Right.
Okay, good. So this is something that we apply later. This is why I recall it. So linear dependence on the Fi alpha lifts to a linear dependence on the power series if you under some circumstances.
Yes. Okay.
Okay. And so the second context in which these M functions come up is in terms of k automatic and k regular sequences. So let me recall that briefly. I am not sure how familiar people are with that. So a sequence is k-automatic if it can be produced by a finite automaton with outputs. So the idea is that you take some number n, you write down its base k representation, and you feed the digits into an automaton, and it produces the value of your sequence at n. So for example, for this 2 and more sequence, this is 2 automatic. Recall that the coefficient is the parity of a number of ones in a binary expansion of n. So if I'm given some number n, I write down the binary expansion, which is a bunch of zeros or ones, and then let's say I start reading from the right. I start here. If I have a 0, I stay here. If I have a 1, I toggle the state. And then again, if I'm at that state and read a 1, I toggle the state. If I read a 0, I stay here. So this, and the output produced is then this label here, 0, 1. So if I read an even number of ones, I will get output 0. If I read an odd number of ones, I will get output 1. And in general, a k-automatic sequence is one that can be produced in that way. And these are classic sequences in theoretical computer science. And see, another one would be this paper folding sequence. And then there's the more general notion of k-regular sequences. What I give here is not the usual definition. So these were introduced in the 90s by Alouche and Chaly. I give a characterization which is a bit more structural here for us. So it's k-regular if, well, again, we look at a base k expansion of n. And now for every digit, we fix some square d by d matrix. And we compute the term of the sequence in the following way. We have some fixed initial starting vector v. And then as we read the digits left from right to left, sorry, we apply these matrices corresponding to the digits to our vector. We end up with some column vector, and we multiply that with a row vector to get a number. And this is the value of the sequence. It can be shown with a different characterization easily that all k-automatic sequences are k-regular, but this is a more general notion because a k-automatic sequence can only take finitely many values according to the states of the automaton. And here, for instance, you could take an to be the number of ones in a binary representation of n. So this is too regular, but not too automatic. And it's known that the k-regular sequences are k-automatic if and only if they take finitely many values.
Can I just confirm that when you write n equals to bm b0 sub k, it's the k expansion?
Yes, I did not say that. Yes.
All right.
Thanks.
Thank you.
Now, how is this connected to m functions? So if we take such a sequence of k-automatic or k-regular sequence and take it as the sequence of coefficients of a power series, then Becker has shown that this always gives an m function. So there are inclusions of k-automatic series and k-regular series. Of course, this one is proper, as we just saw, because they are k-regular series with infinitely many distinct values. And this is also properly contained in the set of m functions. So just to recall again, m functions need not be k-regular, but the converse is true. This was proved by Becker in '94. And he also proved the sort of partial converse. If in fact your m function is k Becker, so that means again that this p0 can be taken to be the constant 1, then actually the power series is k-regular. So somehow we have within this class of m functions the classes of k-automatic and k-regular series, but it is a priori not completely clear how these classes fit in here. So what we set out to do with this paper is to understand exactly how that works. For instance, we know that the k-regular series that only takes finitely many values is k-automatic, and conversely. Now, a question would be, if you have an m function and it only takes finitely many values, is it also k-automatic? And more generally, what we try to do, we try to get the classification of these m functions by their growth, by the asymptotic growth of the coefficients. Of course, the canonical thing to try would be to look at simply the absolute values of the coefficients. But this does not work. So here are 3 examples of such m functions. which all have bounded coefficients in Q. So the first one is actually just a different encoding of the 2 and more sequence with plus and minus 1. This is K automatic. The second one is K regular, but not K automatic, and the coefficients are negative powers of 2, so bounded by 1. And here in the third, we multiply the 2 and more sequence by this geometric series where the coefficients are negative powers of 2 again. So the coefficients are again bounded. So these have a very different structure, but all bounded coefficients in Q. So the absolute value is not the right notion to use here. And this is why we have to use the height. In particular, we use the absolute logarithmic height. And let me recall that. In the simplest case, which in fact you can restrict to in your head if you like, if alpha is rational, non-zero, and we have a reduced fraction representation, a divided by b, then the height is simply the logarithm of the maximum of the two absolute values. So this log is why we say logarithmic height. We are basically taking the maximum of the numerator and the denominator of the reduced one. And more generally, if one has a number field, one has to fix a suitable set of representatives for the non-trivial absolute values. And then one defines it as this a priori infinite product over all absolute values, and we take the maximum of 1 and the absolute value of this number alpha, and then the logarithm of this product. And then actually the absolute value is less than or equal to 1 at all but finitely many of these places. So this is in fact a finite product and well defined. So just to make this a bit more concrete again, if we take k equal to q, then we get the usual Archimedean absolute value, and for every prime we get the absolute value associated to the p-adic valuation. And if you work this out, you get back to this formula above. And we need the few basic properties of this height. The first one is that if you take a non-zero algebraic number, then the height of it is 0 if and only if alpha is a root of unity. And it's also good to know that there's this Northcott property. If you look at algebraic numbers of bounded degree and height, there are only finitely many of them. And this height is somehow for us the useful measure to measure the size of coefficients here. So with that prelude and definitions, I can now actually state our main theorem, which is the following. If we have an M function, then it falls into one of 5 classes, which are determined by the growth of the height of the coefficients. So one always has that of the logarithmic height. The logarithmic height is at most big O of n. But if it is already in little o of n, then it must be in big O of log squared n. So for instance, log cubed n is impossible. So this is the general structure of this theorem. You have some bound in big O, and if the same bound were satisfied with little o, you drop down into the next class. And the classes that there are n, log squared n, log n, log n, and constant. And well, first of all, in each of these 5 classes, there exist examples of M functions. And each of these classes corresponds somehow really to a structural description. So in particular, the one with bounded coefficients in terms of the heights are precisely the K automatic ones. And then there are 2 more classes of K regular sequences. And then there are 2 classes of non-K regular sequences. So each of these gaps actually, so here it's just in terms of asymptotics, but as I said, it corresponds to some kind of structural description. And for this, I need to introduce one more small definition. If we have a K-Mahler power series, then we can look for the GCD of all the P0s that appear in such equations. So, well, this is an ideal. These are the P0s, say, among all K-Mahler equations that appear, and because it's an ideal in the polynomial ring, it's principal, so it has a unique generator if we norm it correctly. And this is what we call the K-Mahler denominator of f of z. So this is the GCD of all the P0s that appear in a K-Mahler equation for f. And So this means that this K-Mahler denominator always divides P0 if you have a Mahler equation for F. But there's one a little bit hairy part. A natural thing to do is to take an equation for F of minimal degree. But then the corresponding P0 might not end up being the actual Mahler denominator. So we have an example here. If you look at this Mahler equation of degree 3, one can show that this has just one solution up to scalars, one non-zero solution up to scalars. And you see here the P0 has a root at 1/2. But one can substitute this equation into itself to eliminate this root. And then you see that actually the K-Mahler denominator is 1. So this series is actually K-Becker. Oops, sorry. Okay. Now with that in hand, let me go to the first gap. So the first gap is saying if the height of coefficients is in little o of n, then every non-zero root of this K-Mahler denominator of this polynomial is actually root of unity. And equivalently, f is analytic in the entire open unit circle for all absolute values. Or equivalently, the height is asymptotically in big O log squared of n. So this is this gap from little o, oops, sorry, where did I go? From little o to big O log squared n. And the structural description is that all the roots, the non-zero roots of the K-Mahler denominator are in fact roots of unity. And in some sense, this first gap is the hardest one because it uses this transcendence series. So the gaps get easier and easier as you get down because you have more structure. I want to at least give you the idea of the proof here. So the assumption is that the heights asymptotically are in little o of n. And we want to show that every non-zero root of the K-Mahler denominator is a root of unity. So what is easy to show is that in this case, the power series has radius of convergence exactly 1 for each of the absolute values. So this is just this square root criterion for the convergence radius. And now assume that we have a root of the K-Mahler denominator, lambda, that is not the root of unity. If it's not the root of unity, it means there exists some absolute value so that the absolute value of lambda is strictly less than 1. So it's strictly in the unit circle. And we want to show that f then must have a pole of lambda, but this would contradict this radius of convergence. So we suppose that f does not have a pole at lambda. And we take a minimal Mahler equation for f. So we take the d minimal. Then one can show with a bit of work that these power series f of z up to f of z raised to k to d minus 1, where the d is coming from here, are in fact linearly independent over the rational function field. And then here we use this linear version of the transcendence result to see that, well, so lambda has absolute value strictly less than 1, so the powers converge to 0. So if we take large enough powers by this transcendence result, also f of lambda k to the n up to f of lambda k to the n plus d minus 1 will be linearly independent over the algebraic closure of the base field. So at this point, we have achieved that these powers of lambdas are linearly independent of k bar. And now what we can do with our equation, we can iterate it, so substitute it into itself. And then here we can produce higher and higher powers of k in the exponents, and the left term just stays f of z, but of course the coefficients change. And then one has to check that one can do this in such a way that these coefficients are still co-prime polynomials. And now the point is that the Mahler, so lambda was a 0 of the Mahler denominator. So it must be a 0 of this R0 because it's a 0 of all these initial terms of a Mahler equation satisfied by f. So if lambda is not a pole of f, we can just plug in lambda into this equation. and this first term will go away because R0 of lambda is 0. And then we get this equation. And because the Ri's are co-prime, actually not all of lambda is not the root of all of them. And so we get the linear dependence between these values. But this is a contradiction to this fact that these values here are actually linearly independent. And so this contradiction implies that fz has a pole at lambda. And then in turn that it's impossible that there's a non-zero root of this Mahler denominator, which is not the root of unity. So this is this key idea for the first gap. And here we really use the transcendence result. I won't bore you with the details of the other gaps, but the second one is then characterized again by the Mahler denominator structurally. So this means the non-zero roots of the Mahler denominator must be roots of unity with order not co-prime with k. So they have a common factor with k. And this would imply that if you keep raising z to some powers kj, you will never arrive back at zeta, sorry. And this is also equivalent to f being k regular. So here the proof is a bit technical. It's really analysis looking at what, say, if you have such a root, what happens analytically if you approach it on a particular sequence and you get a contradiction from that. This is the second gap, and this brings us down into this much better structured class of sequences that are k-regular. So if k is k-regular, then it had some representation with matrices. So for every digit, we picked one square matrix. And if you pick the dimension of this matrix is minimal, then you get a minimal linear representation. And we consider this finitely generated matrix semigroup. And then this next gap, the little o log n, is characterized by this semigroup being tame, which means that every non-zero eigenvalue is actually a root of unity. So every non-zero eigenvalue of a matrix in the semigroup. And again, there is a structural characterization of the sequences. So they are not necessarily k-automatic, but they are somehow obtained as linear combinations of some convolution products of automatic sequences. And the final gap is that if the height of an is actually in little o log n, then this matrix semigroup must be finite and the sequence is k-automatic, and then actually the heights are bounded. So to summarize once more this gap theorem, it shows that the solutions fall into 5 completely distinct classes, which are characterized by the asymptotic growth, but also by some underlying structural properties. And this is the main theorem of our paper. In particular, what you get as a consequence, also if you have a field of characteristics 0 and a k-Mahler series over this field, then the sequence of coefficients is k-automatic if and only if there are finitely many distinct coefficients. So this answers this question if k-regular, so we knew k-regular plus finite implies k-automatic, and now we also know k-Mahler plus finite implies k-automatic. But this does not work in positive characteristic necessarily. This was already known by Becker. And more or less to close with, let me say a word on decidability. So we said in the very beginning that solutions to k-Mahler equations can be specified by finitely many initial coefficients and the equations. So you can ask about computability results. If you can say, if you're given such a solution, can you decide which case you're in? And in fact, these cases are all decidable, which is maybe particularly interesting because there's from the same year a result of Daniel Krenn and Shalit, who showed that if you take a k-regular sequence with values in the rational numbers, but you only look at the usual Archimedean absolute value, then it is undecidable if this sequence is bounded. So if we look at the sequence of heights, we can decide if it's bounded, but if we look just at the sequence of absolute values, it's undecidable. And the basic reason is that we can decide if a finitely generated matrix semigroup is tame, so if all the eigenvalues are roots of unities, but it's actually undecidable if it has whether it has a joint spectral radius less than or equal to 1, which would correspond to this characterization here. So let me just summarize in the last minute. So what we showed is that among the M functions, the automatic and regular ones can be characterized through the asymptotics of the coefficients, if you look at the asymptotics of the height of the coefficients. And we showed that there are 5 distinct growth classes for these M functions, each of which corresponds to some distinct structural property of the underlying sequence. And we also showed that, in fact, it is decidable which of these classes a particular sequence or series falls into. And with that summary, let me thank you for your attention and the questions as well. And yes, that it is.
Thank you, Daniel. So for questions, please unmute yourself and ask, or type them into the chat.
So I have a question. Hi, Daniel.
Hi.
So I would like, I have 2 questions. So there is a notion of size of a differential equation, a linear one. There is also a notion for Q-difference equation, an arithmetic size. And I was wondering if there is something for Mahler equation, so that you can deduce from the size of the coefficients of the minimal equation some arithmetic information on, for instance, some power series solution.
I don't know if there is, but I think this would be interesting. I must say I'm not familiar with this equivalent thing in the setting of differential equations. So if you could send me a
it's not completely equivalent, but you have some, you can have some extra arithmetic information.
So the idea is we would look at the size of the coefficients of this, or of this polynomial somehow.
Taking all the absolute value and also the iterate of the equation in the Q-difference setting. You consider the iterate of the Q-difference equation. So there are some I don't know if this is I was wondering if there was something for Mahler equation. So,
I'm not familiar with such a result. But it might be that I just have missed it. I should add maybe that I just moved into this direction like 2 or 3 years ago. So it is a bit new to me, and I'm not familiar with all the literature, but I think I would have noticed that.
Okay. And my second question is it difficult to find, given a Mahler function, its minimal equation?
This can be done. There is a paper by Boris on this.
This is effective.
This is effective, yes, there's an algorithm to do this.
Okay. So thank you.
Thank you for the questions.
I have a question. It seemed to me that in the proof you gave us of the first case that you really used the Mahler equation and not a Mahler system. Is it possible, if you have, can you go back and forth between Mahler equations and Mahler systems? Is there something like a cyclic vector lemma in this case? Is every Mahler system come from a Mahler equation?
I'm not sure what the cyclic vector lemma is. What you can
I'm sorry. I'm sorry. I said that backwards. Does every Mahler system come from a Mahler equation?
So would that mean that all the solutions to these Mahler systems are solutions to the same Mahler equation? Is that what you're asking? Because if you have a Mahler system, this Mahler function, the solutions all are M functions. And conversely, if you have a Mahler equation, you can turn it into a system
Yes,
Mahler
I can see that, but systems can also be turned into equations.
Yes. So if I have a component vector of a solution to the system, then it is an M function. So it satisfies the Mahler equation.
Oh, okay.
Is that what you were asking, or did I not
Yes.
get?
Yes.
Okay, thank you.
Other questions?
I think Andy was also asking about the equation of the same size, right? Isn't there a cyclic vector lemma in the difference context, just abstracted?
Sorry, can you repeat it again?
Andy mentioned cyclic vector lemma. So cyclic vector lemma allows you to convert a system of linear differential equations into a single scalar equation of the same size.
Okay.
So I was wondering whether there's similar kind of lemma for difference equations abstracted, regardless of it being Mahler or whatever.
Unfortunately, I must say that I don't know.
Charlotte, do you know?
Okay, there is something. Okay, there is some cyclic vector lemma. So it means that starting from a different system, you want to put it via gauge equivalence into a companion form.
Yes.
This is more precise than just saying that a vector of solution is a Mahler function. It's really, you can put the system into a companion matrix form, and it's so you need your operator to be an automorphism, so that you can put the Mahler thing in a context of an automorphism by ramifying the variable x. And then, well, the assumption is you have a field automorphism and that is not periodic. And then you have a cyclic vector lemma. It's due to Michael Singer and I think Peter Hendricks in the difference context. So perhaps a Mahler system could be put in a Mahler equation, but perhaps with some ramification. I don't know.
Thank you.
Other questions? So there's a question by Seda Albrecht in the chat. Just about the statement of the theorem.
It's just
yes, so let me share it again. It actually says one of the following holds.
Maybe I misread and then I was confused. How can these hold at the same time?
So,
okay,
so it's one of the following holds. It's
okay. I'm sorry. Okay, thank you.
A silly question. Hello. If f is a Mahler function, does fz to the k also Mahler? Or is it also Mahler?
Yes, that should be the case.
See, in the equation for f, you have the p0 coefficient, right? Which involves fp. But now with fz to the k, are you sure the p0 would be 0?
I mean, so you would just apply the Mahler operator
or there
to the
might be
equation.
some other equation, that is satisfied.
So it does not necessarily satisfy the same equation if that was the question.
Right. So is it Mahler? I mean, it's not obvious. It is.
It's not obvious.
But what's the problem? Take z to the k everywhere in the coefficients. But can't we just take z to the k now everywhere in the coefficients as well? So if there was a question of z, we take the same equation, but substitute z to the k everywhere, because I mean the Mahler operator.
Yeah, but the Mahler operator is not multiplicative.
Yeah, but I guess it doesn't commute it raising to other power, like raising to power k and raising to power whatever in the Mahler, right? It's kind of should commute. No, and maybe I'm missing something simple.
Yeah, this seems like it's just you have a difference operator sigma. You just put it everywhere.
Well, I mean, see if you, so if I let G to be f of z to the k, so does G satisfy a Mahler equation? That's the question. And it doesn't seem obvious to me that it does. And if it does, how to find it?
Yeah, so what I was suggesting is you take the Mahler equation for f,
Right?
take its coefficient, and replace z to z power k everywhere. Why wouldn't this work?
No, because
two Mahler operators, they commute. K Mahler and L Mahler, they commute, right?
Oh, I see. You're saying you're simply just taking the same equation and substitute z to the z to the k. Is that correct?
Yeah.
But then, okay. But then it's not the same form, isn't it?
Well, you have a sigma. You just insert it everywhere. The home office. What's wrong with that?
Yeah, that should work.
Okay. Oh, so you're replacing the pi of z to pi of z to the k. Is that correct?
Correct.
Mhm.
Okay. Yeah. All right. Okay. So that's all. Yes, then. Thank you.
Yeah, please, Charlotte.
Sorry, if I may. So you have a nice combinatorial characterization of k-automatic and k-regular sequences. I was wondering if you can imagine some novel arithmetic, novel combinatorial description of some subclasses, intermediate subclasses between k-regular and Mahler. I don't know, with your height description, have you seen, I don't know, some nice new classes?
I mean, the main thing that I think is new are these linear combinations of word convolution products. Let me share that again. But this is within the regular ones. So this is wait. This is can you see that? Yeah, I think so.
Yeah.
So these k-regular sequences, they split into two classes here. The ones where the height is bounded by log n and the ones where it's by log n. And the log n's have a particular form that, where was that? So they're linear combinations of word convolution products. A word convolution product of a k-automatic sequence is, so at the number n, you again write n in the base k representation, and then you split up this base k representation at every possible point, and you do the convolution over that. That is what we mean by word convolution product. And then you can have word convolution products of these k-automatic sequences and linear combinations of that. And this precisely corresponds to this class here. That is new to my knowledge. The upper two classes, I'm not aware of a combinatorial description. So these are here really just by the positions of the zeros of the K-Mahler denominator.
Okay, but well, you have new subclasses in the k-regular case that are distinguished by this height asymptotic. So it's really nice.
Yes.
So, thank you.
Okay, so I just type a question in as a follow-up for the substitution of z to the z to the k. So basically, the sequence for f z to the k would be different because the powers are spaced, right? So there are a lot of zeros inserted between the original coefficients. So as a sequence of coefficients, how would that affect the height and your theorem, the gap theorem.
Ah, that's a good question. So they possibly grow slower.
Yeah, they grow a lot slower,
Yeah.
and there are lots of zeros in between, right?
Yeah. So you might actually get a more regular structure then.
I think they should stay in the same class.
Do they stay in the same class, Jason?
Yeah.
Okay.
I think so. I mean, right.
Well, when you look at the height, you look at the maximum. I forgot exactly the definition of height.
So it's the log of the maximum of the reduced numerator and denominator. But so if it's an integer, it's just the log of the absolute value actually.
Okay, so maybe it should be the same then.
Yeah, I mean, if you look at, say, the first class, right, that's saying if you're integer coefficients, or positive integer coefficients, it's saying you're growing, you know, often like c to the n for some positive integer c. And now you'd just be growing like c to the n over k. But the c would be bigger than 1. But c to the 1 over k is still bigger than 1. So you're still growing exponentially.
But suppose you have the binary situation 0 and 1, where the Mahler function satisfies such, I mean, t to the n, right, as coefficient. The number of zeros in n. Now, but you change it by the substitution z to the k, or z to the c squared in that case, then it won't no longer be the binary. I mean, the zeros that are inserted would not be the binary representation of n at that place, right? So how could it mean the same thing?
No, but like you would get a different k-automatic sequence.
Right.
But the k-automatic sequences are in the same class.
It will be in the same class.
Like and I mean, in any case, the k-automatic one is the smallest class, like the bounded coefficients. So let me share that again. So the k-automatic one is already here, so you cannot get smaller.
Ah, okay. In that case, all right.
So this just means that if you have
in
integer
general,
coefficients, it just means that the coefficients are bounded, or finitely many. Sorry. And that does not change if you space them out further, of course.
Okay. Thank you.
Any other questions? Well, thank you, Daniel, for talking and answering the questions. So and now we can stop the recording and